Think about what happens when you step outside into the bright sun. Well, certainly that, but also you immediately squint, your pupils contract, and you shield your eyes with your arm. When you bring your arm down and look around, your eyes instantly focus on what you're looking at, even if the thing is very far away. If you now step into a darker room, you have to wait for minutes before you can see properly. Outside, you squinting, your pupils contracting, and your vision focusing all happen, literally in a blink of an eye. But why is that when you step into a darker room, it takes so long? So, grab onto your carrots, wear your eye patches, and ready your red flashlights, because we're gonna take a look at how we see in the dark. Before we talk about how we see in the dark, we should talk about how we see at all. Here's an oversimplified version of it, and I will put the caveats in the description. When light enters your eyes, it hits the retina, which is a screen at the back of your eyeball. Your retina contains these cells called rod cells, which uncreatively describes what they look like. These rod cells, in their upper half, contain a protein called rhodopsin, which will be the protagonist of our story. The rhodopsin protein has this structure, and inside of it sits, quite snugly, a little molecule called retinal. The light that enters your eyeball hits the retinal and causes it to change shape. Pissed off by this uncalled disturbance, retinal changes its structure and leaves the rhodopsin protein. Like a mid-20s dude after a breakup, rhodopsin becomes what biochemists call activated, and it starts a cascade of other proteins and ions that eventually decrease the amount of transmitter going out at the end of the rod cell. Yes, you heard me right. The output signal decreases, which means it is lower in light and higher in darkness. There is a nice evolutionary explanation for this, which this paper sums up perfectly. The biological role of this apparent inversion was soon understood as we realized that reacting to a sudden shadow may be more important for a fish or a tadpole than reacting to increasing brightness. The purpose of this transmitter is to turn the next cell off. So, to turn the next cell on and send signals to the brain, we need to reduce the amount of transmitters coming out of the rod cell. Once this cascade is completed, which takes about a second, the rhodopsin goes back to doing nothing. And that is how we see light. Remember the retinal that got ejected? Well, it goes for a long walk behind the retina, changes back to its original shape, comes back and reunites with an activated rhodopsin, which consequently deactivates the rhodopsin. This process of reunion is really important, but also is pretty slow. When there is light outside, a lot of retinals are being ejected out of rhodopsins. Simultaneously, retinals and rhodopsins are also being reunited, but although at a much slower rate. This puts the system in a state of equilibrium where a small percentage of rhodopsins have retinal in them, while the rest do not. A dark room doesn't have enough light hitting your eyes, which in this case means that the chance of light ejecting a retinal are pretty slim. So, we are unable to see anything. It is only when more retinals come back into rhodopsins that light can finally hit them again and start this process all over. Our eyes can take about 2 hours to adapt fully because the reunion process is just that slow. We have only talked about the biochemical process of adaptation, but there's also a neural aspect, which we might cover in a later video. Till then, stay tuned and thanks for watching.